We present a novel, generalizable, fully automated layout planning framework for robotic work cells, designed to integrate detailed task, grasp, and motion planning within a true 3D spatial context. This system is validated not only through simulations, but also with real-world implementation, ensuring both practicality and reliability. Designing efficient, task-aware robotic work cells is a complex challenge. Traditional approaches struggle with layout feasibility and scalability. They also lack manipulation task and grasp integration. Achieving a compact layout that simultaneously guarantees successful execution of manipulation tasks, without requiring any post-adjustments, is a really challenging endeavor. Our objective is to develop an automated 3D layout planning system that not only minimizes occupied space and operation time, but also ensures task feasibility and real-world applicability for diverse types of work cells. To support integration into various robotic platforms and planning pipelines, we developed a clean and modular API for the layout planner, where the user can define work cell 3D dimensions, upload the STL files for layout components, change component orientation, and also define robotic manipulation task. And for more applicable implementation, we enable the user to add relational constraints between the components, like a coincident relation between a shelf and a table. And the user can hit the Layout Presentation button to visualize the current uploaded components and check the defined constraints. Moreover, you can hit the Optimize button to see an optimal placement for each component with manipulation task execution in simulation. Behind the Optimization button, we propose a hybrid evolutionary framework integrating NSGA2 with PSO, enhanced by a surrogate model to accelerate convergence. Our approach embeds task, grasp, and motion constraints directly into the optimization loop. The framework generalizes across various layouts and robotic configurations, showcasing robustness, reconfigurability, and scalability for industrial applications. And as you can see, not only the optimal placement resulted but also the task execution for each workpiece. To validate the practicality of our proposed framework, we deployed the optimized layout in a real-world robotic work cell. The cell was built using the exact component arrangement generated by the planner, without any manual adjustment. The robot successfully executed the manipulation tasks, confirming that the layout not only meets theoretical constraints but also performs reliably under real conditions. The proposed system has been evaluated from some key perspectives to demonstrate the effectiveness of the algorithm. First, to evaluate the robustness of our optimization framework, we conducted a suboptimality test. This was done by benchmarking it against a surrogate model which is learning-based to identify potential convergence issues. This test serves a dual purpose. It reveals if the optimizer converges prematurely to suboptimal solutions, and it assesses the fidelity of the surrogate model in capturing the true objective landscape. Second, we have tried to select a work cell that has more than 2 manipulated objects and has a complex manipulation task like unscrewing a box lid and sort geometrically different objects. For this work cell, we evaluated 3 methods: Baseline A, a 2D layout optimization with only collision constraints, no overlap, without task feasibility. Baseline B, a 2D layout optimization with collision and robot reachability constraints. Proposed, a 3D layout optimization with full task motion grasp constraints, allowing intercomponent overlap. Result shows that the proposed method significantly outperformed both baselines across all metrics. Notably, only the proposed approach produced a layout where the full manipulation task was executable without additional reconfiguration. Finally, a comparative analysis is conducted between the proposed meta-heuristic approach and a learning-based algorithm under identical conditions to benchmark performance. Reinforcement learning was not able to realize a policy for a compact and task-constrained layout. Results demonstrate the superiority, practicality, and reliability of our method for real-world robotic work cell design. This is the end of our video. Thank you for watching.